Okay, we're looking at the problems from time functions, and we're going to start by trying to find the maximum speed of the oscillator's motion. We can do this with conservation of energy if we know what kind of oscillator it is. We can even do it without knowing what kind of oscillator it is, and a bunch of things will cancel out. But if we have the graph, we know the frequency and the amplitude from the graph. These are all the values that I got from the graph. Yours may be a little bit different, so we might disagree on some of the numbers here. The frequency I got from doing 4 cycles across the graph and measuring the time for that so that I could get a nice, pretty accurate number. So anyway, if I know the frequency and the amplitude, what I want to use is the fact that I know that my v of t function from our derivation in class is 2 pi f times the amplitude times the cosine of 2 pi f t. So the maximum value of this function is, it's like the amplitude for the velocity function. So it's not really an amplitude, but it is the max value. Is that little bit out in front. So this is exactly what we would get if we used conservation of energy for the oscillator to do it, but it gives us slightly different quantities here. So 2 pi f times the amplitude is our maximum speed, which is, I got about 0.475 meters per second. It should be somewhere around 0.5 meters per second, depending on what your numbers are. Similarly, we can find the acceleration function using f and a. And so the maximum value of that is, again, the bit that's out front. And you can also do this, if you know the spring constant, you know how far it's stretched. It's pretty easy to figure out what the acceleration is from the f-net. But this will work too. So you just want to pick the best method depending on what you have. Okay, so 6.45 meters per second squared is our max acceleration. Okay, so now we're trying to talk about whether if it's a specific kind of oscillator. If it's a spring oscillator with 50-gram mass, it doesn't matter if it's horizontal or vertical. The relationship between frequency and mass and all that are the same no matter what. So we have the frequency of a spring oscillator is 1 over 2 pi root k over m. You could also work from the period equation. It doesn't really matter. Either way, you're going to solve for solve for k. So the k is, I'm going to bring the 2 pi over, square both those, so 4 pi squared and f squared, and then I have to multiply the m up and check those units and use your newtons being equivalent to kilogram meter per second squared to figure out that everything works okay. And I get about 9.2 newtons per meter, which is not a terribly stiff spring. Okay, so if it's a horizontal one, we want to look at we're going to figure out the resting length of the spring, assuming that what we know from the graph is the length of the spring. So what we were given on the graph is that the x min is about 51 centimeters, and the x max is about 58 centimeters. So the x at equilibrium is 54.5 centimeters. And if this is a horizontal spring, the equilibrium point is also where the spring is not stretched at all. So that must be the natural length. Okay, as if it were stretched at equilibrium, there's no other force opposing it, it would accelerate, which means it's not equilibrium point. If it's vertical, the picture's different. The maximum stretch is here. This is the equilibrium stretch. Okay, so we know that at the equilibrium stretch times k balances mg. So since I know mg and k, I can calculate that to be 5.4 centimeters. So I put all my numbers in SI units and then move the decimal place to get it into centimeters. So that tells me that at equilibrium, that 54.5 centimeter spring is stretched 5.4 centimeters, which means that its natural length is shorter than that. It's shorter than that 54.5. It's 49.1 centimeters. So it's a little bit stretched even up at the top when the spring is 3.5 centimeters shorter. That still doesn't get you back to natural length, because that's how it goes with these vertical springs. So remember, the midpoint is the place where the forces add to 0. And now for pendulum, the length and the maximum angle of swing, I'm going to do the length first. So for a pendulum, the frequency is 1 over 2 pi root g over L. So I can solve for the length from that, just like I did in the previous equation. And I'm going to get g over 4 pi squared f squared. And if I plug in the numbers there, I get 5.4 centimeters again. That's a kind of a pretty much a coincidence up there. Yeah, these two values are the same. Knowing that the pendulum is 5.4 centimeters long, and knowing that the length on this side, which is the amplitude, the maximum distance here is 3.5 centimeters. I want this angle. I can just use the definition of sine. So sine theta is opposite over hypotenuse, so A over L. I can solve then pretty easily. Theta is inverse sine of A over L, which gives us about 40 degrees, which is really a little bit further than we should go for our, that is okay for our frequency expression here. Remember, we want a small amplitude, maybe about 30 degrees, but that's okay. So we have a model here that gives us a decent result. It's just not perfect, but that's okay. That's the best we have right now, and that'll do it for us.